So remember, one thing we did, I'm still thinking in the Cauchy formulation. I'm still thinking that we have labeled our space-time with a sequence of space-like hypersurfaces. But there was a great question at the end of last lecture. We said, well, isn't this weird that we're thinking that we have this foliation of space-like hypersurface of a space-time that we're constructing as we go? So how do we know that this makes sense? And it is a tricky way of interpreting this, but I mean, let's see if we can get on the same page. The fact that I have made these slices here, and I'm labeling, let's say, 1 times 1 times 10 times 100, it doesn't mean that the space-time looks like this. As we evolve, we're going to have to continuously ask questions, is what's going on with this one? So let me just give you the example of that you saw with Malcolm. So suppose you have a star that collapses, forms a black hole, forms a singularity. Then we have a black hole like so. And let's say you're trying to study this situation. So you may choose some slices. I mean, there are lots of space-like hypersurfaces here. I mean, I can do something like this. Sorry, this goes in this way. And these are our slices. Then we're proceeding to forward to the future. Another thing we have to do as we go along is to ask what's going on in the space-time. So as we're constructing it, we can compute, for instance, curvature scalars. And the curvature scalar here will be perfectly well behaved in this hypersurface as well. But as we get to here, we're going to begin to see that there is a region where it begins to be, the curvature begins to be very, very large, arbitrarily large. So we're beginning to go about to run into the singularity. If we do run into the singularity, things are going to blow up. So it might be that we can evolve from here to here, but then around this piece, something is just amiss. And then we do what we said we're going to be careful with. We throw in more resolution, we decrease our time stepping, we do everything we need to do numerically to convince us that this is not a fluke, it's not an artifact of the numerical implementation that's going wrong. This is physics, something is going on, and then we're going to have to interpret, oh, maybe what we're doing is truly running into the singularity. This is to say, again, this is an opportunity to say, having something that is well posed doesn't mean that the solution cannot blow up. The solution can blow up. What the well posedness will say is that there is a clear conversion behavior to a solution that is divergent. And so you need to convince yourself first and everyone else afterwards that this is what you're seeing. And if you have such a slicing, that's precisely what will happen. However, something that we'll cover a little bit more today, the lapse and the shift is something we can choose. So that might be, this was a slicing that ran into the singularity. But let's say you're still interested in what's going on up here. So another type of slicing that you might choose is to have, say, slices that are very much like the ones we have here, but after a while, then this one actually bends. All along means space-like. So what you're doing is slowing down the rate of time, the true rate of time. So here, my foliation will still might have the same labels, 1, 10, 100. But if you compute the proper time as I move in this direction, this is barely changing as I go from 1 to 10, while far out is changing a lot. So this is a way to kind of use the freedom you have in your labs to delay kind of hitting a problematic region while you can explore things in the other direction. There is, however, a price to pay, and there was a question, right, some of you came in the room, which was, well, what is the impact that that's going to have? Well, as you have such a bent kind of hypersurface, you're going to begin to see you're running out of resolution. You need to add more and more points to resolve this region, which may require also to have smaller and smaller time steps. So these are practical things that you're going to learn as you go, remember, if you're solving a problem numerically, it's because you don't know the answer to begin with. You're exploring, you're creating, constructing the space-time as you go along, and it's no telling what you're going to find. So you have to be asking the right questions as you go along. There's another thing you can choose doing, which is to ask the question, is there a black hole? Here I'm jumping ahead, but is there a black hole? Because if there is a black hole, maybe I can do other things. Maybe I can say, let me keep that slide. Hopefully you're not going to see it. Have something like this. But if there is a black hole, maybe I can go some distance in and stop my simulation there. I mean, I just take it away. There is this technique called black hole excision, which basically says, if you know, assuming that you can prove that there is a black hole that has been formed, or that there should be a black hole within a region, and your lapse and shift conditions are such that everything, and I will give you an explicit example of this, are ensuring that everything is inflowing within that boundary, then you can say, I'm going to stop my simulation. So let me make that cleaner in a different plot. Suppose this is now the emanating event horizon of the black hole. These are your slicings. Before, they were going all the way, say, to r equal to 0. But now you come in here, and I'll tell you in a second how would you know. You could argue, wait, I'm already inside the black hole, so maybe I can stop my simulation there. Maybe I can stop it there. Maybe I can stop it there, etc. So you choose to not evolve some piece, some portion of the space-time that is inside the black hole because you're interested, say, in observational features that, of course, would live outside the black hole. You may, however, be interested in what's going on inside of here. You're trying to ask questions about, say, mass inflations in rotating black holes. This is a problem by, say, those nicely illustrated and pointed out by Israel and Poisson. That would not be a good, sensible thing to do, to excise. You might want to push as much as possible, being very close to the singularity to try and answer questions. But if you're interested, say, in gravitational waves that light will be measuring, you can excise the black hole. I'll tell you another option that you can have later today, which does not require an excision, but relies on going kind of to the R quadrant in an effective Penrose diagram. But this is something that a priori you might not know. You have to keep asking questions dynamically as your simulation goes on to try and infer what the properties of your solution are. So before we go and discuss some of those features, let me backtrack a little bit. And remember, at the end of yesterday's lecture, we made contact with this generalized harmonic formulation of general relativity. And the reason I'm leading with that is because, well, we knew the ADM formulation had an issue. We also knew, I hope you fell in love with the nice properties of wave equations. And we discussed that if we look at, say, the Ricci tensor, we almost had a wave equation if it weren't for that extra thing in there, which also had higher secondary order derivatives. And I mentioned that the proof of well-posedness by Yvonne Choquet-Broad realized that, oh, I have 4 coordinates freedom, I can set this to 0, and if I do, then I have a nice wave equation and everything proceeded. So the same thing happened on the numerical level. You can say I can set it to 0, and then you have a nice set of equations. But then you say, well, but maybe I want the freedom back. And so one option you can say is to say, well, there are some functions that we'll have to discuss how we define them. But let's say there are some a priori given functions or have functions that have also some dynamical definition associated to them, but in a way that is very nice or to ensure that things will be well posed. Let's imagine for the time being that they are God-given. So this, if I'm setting the coordinates or the trace of the Christoffel symbols being equal to these sources, and I make sure I preserve that through my evolution, this is something I have to do because what I'm doing is I'm getting rid of that term and replacing it by the grad of the h. Then what we have is a constraint. that is that. So it better be that gamma minus h be 0. So you can, it's just one line argument to say, well, if I'm replacing gamma by h, what I'm doing is essentially thinking that this is the equation I have. RAB with the gamma is nothing but the covariant derivative of C with the symmetrization. So if we put this in here, use the definition of gamma, you will see that grad of gamma will cancel that. You're going to have minus grad of h. You send it to the right-hand side, and that's precisely what you're saying you're doing. I'm replacing the gamma by the h. Then you can ask the question, will this be preserved? Given that I have this constraint, and I'm solving the evolution equations this way, will I preserve C being 0? Is this natural? So it's the same thing as we said in the case of ADMs, that you could prove. I mentioned you can say, if I use the evolution equations and I satisfy the constraints initially, would they stay satisfied? So this is what you do. Remember, the Einstein tensor satisfies Bianchi identity, so if I take the covariant derivative of this, I should get a 0. So this, I leave it as an exercise, but it's a very simple few steps derivation. Start from here, replace this, and carry through, assuming that your RAB, your Einstein equations are given by this. And what you will arrive is the following feature, that the double covariant derivative of C, this is like a box operator acting on C, is equal to something that is proportional to C. So that tells you again, if C is initially 0, these equations will propagate as 0, and you're satisfying the constraint. But we mentioned that we may want more than that. We want a feature that if we are slightly violating the constraints, we want to see if we can push them back to the constraint surface. So then let's suggest that we change these, which we said were Einstein's equations with our choice gamma equal to h, with that. RAB equal to the same as before, but let me throw in this extra term, which is proportional to C. So I'm not changing the equations at the analytical level if I'm satisfying the constraints to begin with. Go through the same exercise, and for sake of the argument, imagine just keeping the equation to linear order in C. So if you see a C square, just throw it away. You're imagining that your initial error is very small. You can do it to all orders, but I mean, for the sake of this argument, let's just keep it linear order C. So if you put this, you go again through the same derivation, now your equation changes to that. So it's box of C. Remember, if I said we're keeping to linear order in C, this is gone because it's proportional to C squared. So the equation is kind of the box equation on the C is equal to this piece. This piece has in particular this contribution, which is the derivative, if you want, along n, and if n is our normal that is time-lag, this is the time derivative of C, and then something that is proportional to C. So this looks like the following equation. Like C, let's imagine just locally in space, C double dot could be, kappa is a constant that we can just use, define in any way we want. So let's say it goes like kappa C dot plus kappa C. And you can very easily convince yourself by analyzing what the solution to this equation would be, is that you can choose the kappa sign so that this is a decaying thing. It's a decay exponential. So this is a technique called constraint damping. Which achieves precisely what we wanted. If we have an initial small violation of the constraints, or numerically, as we evolve, we see the little bit of failure, this continuously pushes back. And as I said, this was crucial to get the binary black hole or generical black hole solutions or simulations to behave well. I mentioned this formulation CC-Z4. So the CC-Z4, and I can't remember what the terminology or what the reasons for this thing is. There's a formulation that initially was called the Z4 formulation by Carles Bona, Valenzuela and company. and then was kind of adapted so that made contact with the BSSN formulation. But anyway, so this one says, let's start with that equation to begin with so that by construction, we have the ability to dump constraints, and let's make contact with BSSN, which itself made contact with ADM. So remember we discussed what the key issue with the problem, was the problem behind the ADM formulation not being nice, which had to do with, we had an equation of motion for our intrinsic metric that was given by the 3 Riemann tensor, Ricci tensor, and this Ricci tensor had exactly the same problem. So there you would have things that go like, let's say, gamma Lm, dl dm, gamma ij, plus di gamma 3j symmetrized. So the BSSM formulation says, this is offending. This is I don't like. It's breaking my nice wave equation. Let's do something with it. So rather than saying, let's use, let's just explicitly change this by some known functions, it says, let's try and have a new evolution for the gamma. And you can induce one by using the momentum constraint. Plus some particular choices for the lapse function evolution. So they have a dynamical prescription for the lapse function evolution. That basically is what makes the BSSN formulation. But if you actually construct it to begin with, if you go through the ADM derivation again, not starting with from RAB equals 0, but starting from RAB equal to that, you also can build in explicit constraint damping in your system. I will not go through all the details because we're going to run out of time just by discussing this. There are plenty of good resources where you can read this. I highly recommend the notes I mentioned yesterday by Sebastiano Bernuzzi. He does a very clean job going through the derivation. If you have any questions, let me know. This is in all cases. But I told you what the key thing is that made a huge difference in the implementation of the equations. I should say that the failure of the ADM formulation to leading to a well-posed system, the failure of it being strongly hyperbolic, shows up only when you're in full generality, if you're doing a 3+1 problem. If you insist of using some symmetry, if you're solving a symmetrical problem, maybe axisymmetry, the breaking doesn't show up. So it's special when you have sufficiently general problems. So this is a reason why for a very long time, the ADM formulation was perfectly good for problems that people were trying. Only when people started trying to do the collision of black holes, things were just completely misbehaving. So it could be that formulations that are not very well suited in general might be just fine in very specific setups. So any questions on this? Yes. Oh, sorry.
Thank you. I wanted to ask, so you said that in the BSSN formulation, it's standard to use a certain choice of lapse function. So what do people use? What is the logic?
Yeah, I'll get to there in a second when I discuss a bit of that. And also there is the momentum constraint also leads you into a rather special, if you want, condition for the shift. So, so in some sense, the BSSN formulation is, and it's related CCZ4, is a little bit restricted on the gauge. So it tells you, oh, you want these particular gauges, which are the ones that will be convenient because we're actually using the momentum constraint. The BSSN originally did not have explicit constraint damping, but by using the momentum constraint in this way with that gauge, the shift condition implicitly was also trying to help push the constraint to decay.
Maybe just one more question. do you use, for instance, sorry for that. Do you use BSSN, for instance, if you expect the causal structure of your space-time to be in a certain way? Let's say, okay, you have initial data, you expect it to evolve to a black hole, for instance. What is there a difference in what method you would?
No, great question, and let me try and answer it. That's a nice segue in what I wanted to say next. So the question, let me try and rephrase it, perhaps more in my terms. If I'm working with this problem or an R1, is there a particular formulation I would prefer? My answer would be no, not at all. And I think with one exception, and this is exception of the instability of black strings, all other problems that people are working on by and large have been solved with both formulations. Like, for instance, the spectral code uses generalized harmonic formulation. Franz Pretorius codes uses generalized harmonic formulations. The codes that have been using, depending on the problem, I do one or the R1. And most other people are kind of either BSSN or now the CCZ4. The CCZ4 is essentially the BSSN with the constraint damping. But what's the key difference has to do with this? So let me just go back. Oh, and also there are applications in cosmology. By and large, those have been done with generalized harmonic. So let's imagine we're doing Schwarzschild. The typical gauge conditions used in BSSN want a slicing that is of this sort. In some sense, this is what they're doing. So they go inside the black hole and they connect to the other, either go to I plus or they go to the other I naught. By doing so, they do away with excision. They never run into the singularity. This tells you already that your labs better not advance much, like in here, because otherwise you're going to get very close to the singularity. So what's the typical gauge condition that is being used there? It's something called the family of 1 plus log. So let me just roughly tell you that you have, these are things like so, where just let's think physically what some condition like this will do. It will tell me alpha, the lapse, and put a minus sign. So I'm going to slow it down if alpha wants to be large, and especially if the extrinsic curvature wants to be large. So if my foliation gets to get close enough to the singularity, I'm going to put the damper on it. So it's very, very much slowing down. And then the shift condition, let me just, basically says, tie the evolution of your shift with the behavior of the Christoffel symbol, roughly. So it says, okay, if my Christoffel symbol is beginning to behave very different from what, say, small weak fields, the shift begins to react. And what it's trying to do is push points around. I'll give you an example why. So that the effective discretization length of points inside the horizon is not running out of resolution. So let me just give this example again. Suppose we have this star that is collapsing, and somewhere here we have problems. So I can have the following slicing. So all good. And then what this is going to be doing is like so. Because I don't want to go past that point where a singularity arises. However, if I keep the same resolution, the same distance in between, the effective distance between points constant, what I find is that this point would be a very large distance between neighboring points. I'm running out of resolution. So this shift begins to move points around effectively so that your resolution is not, in practical terms, is not significantly degraded. And this is getting that job done. The same problem done more on the typical ways that a harmonic formulation will do we'll choose a foliation that goes like so, but then it stops there. And this is how you get away from problems. So the question now is that how do you even know it's there, given that event horizon is a teleological thing? It's something that you only know where it is a posteriori. So in practice, what you do is do something else. Is you ask the question about apparent horizons. So an apparent horizon is something that you can ask, does it exist on a given slice? An apparent horizon is, let's take one arbitrary slice, and then we ask the following question. Can we define wherever some surface on that slice such that if I compute the divergence of the outgoing normal, so I have a normal that is null, let's call this L, which we have to construct. That normal in general, we can write it as NA plus SA, say if we want to normalize it divided by 2. We have the right normalization, where S is the normal to that surface within the hypersurface. That would be the S. That would be the N, the normal to our hypersurface. And we ask the question, that's the right projection of the outgoing divergence of null normals onto that surface. How does it behave? Is it trapped or is it not? So what you are really asking, let me just make sure I don't make a mistake, is if, let's imagine I define the following tensor, which is the projection, and it's a projection fully to that surface. So remember, we had this projection, gamma AB was GAB plus NA MB. That projects any vector in my space-time to be tangential to the hypersurface. But I also want it to be tangential to that surface within that hypersurface, so we need to throw in, and that would be my projection, let's call it. That's a projection of any vector onto the hypersurface, onto that surface. If I use that, and then I ask the trace of that object, that's going to be theta, which is the expansion of so an apparent horizon is defined by the condition, let me first, a trap surface so that surface will be trapped if theta is less or equal to 0. And of course, the marginally trapped surface is for theta equal to 0. And then the outermost, because there might be many, marginally trapped surface is what we define as an apparent horizon. And then you can prove, what you can prove is if your space-time will have an event horizon, all trapped surfaces, marginally trapped surfaces, or all trapped surfaces will be inside of it. So at any given hypersurface, you could ask that question. Is there a surface that is necessarily within an event horizon? If you actually write down what this is, this theta is given by the divergence of that vector on that hypersurface plus the product of the extrinsic curvature of the hypersurface with that normal vector minus the trace of k. So that's what you're looking. Is this thing for the surface negative or positive? Of course, that begs many questions. Okay, this says, find me that surface. It could be anywhere. Because if you have objects here, this related to your question, where is it that my trap surface might lie? So this is how you try and go and place, because I can use this surface, that surface, and I have to start looking all around. So in practice, you know where you have more of gravitating systems, or if you have put stars or something that bends your spacetime here more than otherwise, so you're going to begin looking around this region. And there are many methods out there. There's an excellent review by Jonathan Thornburg that tells you all the options that people are pursuing. But typically what you do is just you look around where you think it is. You start, say, with a large surface. Of course, in that case, the expansion will be positive, and you make it smaller and smaller and smaller till you find that outermost trap surface. Once you find that, you know that you're going to be inside the horizon, and you can decide to excise everything that is inside, provided your gauge conditions are correct. Yes? No, thank you. Is it on?
I just wanted to ask, I mean, as you were saying, when you have an event horizon in your slice, I mean, you have these apparent horizons, which and you have marginally trapped surfaces inside. But I guess very often the contrary question would be of interest, right? You have some initial data set, you have apparent horizons, but I mean, with numerics, you can never, I mean, get everything. I mean, you cannot evolve forever. I mean, you don't have the same, right? I mean, you don't have the same knowledge as you would have if you do it analytically, where you have, you know, everything. You have your entire Penrose diagram, and you define the event horizon through the causal path of scry.
Okay.
So I guess what I'm asking is there some kind of theorem, if you have apparent horizons and you have certain conditions, that this gives you an actual event horizon?
Okay, so the theorem, so we do have theorems. Let me just push back. I mean, I know, and I agree 100% with what you said, but just let's push back, because I'm channeling my inner Matt Chopwick. There is no difference between numerics and analytics. If you do the numerics as carefully as you can make an argument. After all, how do we know pi? We know pi, there is an infinite series, and at some point we say, well, we know it this well, but we actually evaluate it numerically. But no, but I agree where you're going. But let's say, at the analytical level, we know that if we have an apparent horizon, it will be inside an event horizon. You might still not know what event horizon is. For that, you're going to have to keep evolving. And then you ask the question, where is my event horizon? And you can go finding it by tracing null rays, seeing where they have maybe an accumulation points. But what else was in your question? Let me think. Because here you're constructing the space-time. So if I go again with this example, so here you have the singularity. Here you have your end horizon, let's say. So you're going to keep going. And at some point, say your slice was up to here, and then you work to get some slicing this way, because you cannot go all the way to scry. You just don't have access to that. But at this slice, let's say whatever is my furthermost slice I can get to, I can start tracing null rays to the path. And so all those diverge. Right, so I start a null ray here, kind of would correspond to that one. And then I will see that some hover in some region for a very long time, and then they peel off. And so then you begin to build this Penrose diagram at the practical level with the space-time you have.
Yeah. I mean, I see what you mean. I just feel like you never exactly can make contact, right, as you were saying, because you never reach scry completely. And
Good.
that's what you need in your form. Usually in the textbook formal definition of a black hole, right? You need a well-defined notion of scry, but when you do it numerically, you can never quite get to scry.
You can get to very close, and depending on the formulation, you might get very darn close. So this is a space-like formulation. Let's imagine the same construction, but instead of using space-like surfaces, I'm going to use something else. I'm going to use a null formulation. So I can start this way, and then I go. So all the time, so this is my time like null. So I go from here all the way to, I can go all the way to scry. So I'm actually filling all this. Of course, at some point, what you're going to get is once you get very close, you're going to see that your time step becomes impossibly small. Things are beginning to get very large. The redshift here is diverging because you're getting very, very close to the horizon. But for all intern purposes, you can get as close and build the case as strongly as possible to say, this is what I have. Of course, now that I'm getting here, I cannot go past this. So I might have to change my formulation to try and see if I can fill in this piece. Alternatively, let's do this in a different way. I want to use, rather than doing this, I might be able to use this kind of slicing. Right? So this slicing, so now I'm advancing this way. Tuck, 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 tuck. And so all the way I'm getting up to here, got to there, but now this ray just hit a singularity. So I explore a little bit of the inside. Here I might have to excise because I can't go too close, and I can build enough of here to try and get a reasonable good sense of what's going on in this case. But I agree, I mean, if you want to have absolute control, well, numerics can only take you so far, but hopefully you can gain enough intuition to paint this picture.
Thanks a lot.
Any other question?
Yeah.
Yes.
So if you find an apparent horizon, then you say you can just evolve what's outside of it.
If your main interest is what's going on,
Sure.
that observers will reach, yes.
But how do you, because what's going on, what's inside the horizon affects what's outside as well. So how do you encode that into?
So, okay, at the analytical level, we're doing classical GR. So
Yeah.
whatever is happening inside cannot affect what happens outside. But how do we ensure that we are actually getting that? Because otherwise you may actually get some leakage from the inside out, just out of purely numerical issues. Is that what you're asking?
Yeah, I mean, like if something falls in, it somehow, now the black hole has a bigger mass, which then I guess affects the surface that you're evolving.
Yes, but I mean, you remember this, the apparent horizon is contained inside the event horizon.
Oh, okay.
So what you always do is go, this your apparent, because you don't know what event horizon is, you just know that it's inside. Only in equilibrium, the apparent horizon and the event horizon will coincide. So if there is dynamics, you are doomed to be slightly inside. Then you go a bit more inside so that you have some buffer room, and then you stop there. And then you can keep that boundary there, or you can make it march out ever so slowly. So if you see that your apparent horizon got twice as big, then you can make that inner boundary twice as big. But you only are in lockstep, I mean, you could imagine doing that, so that you always have some distance inside of it. But it still doesn't mean that you're doing the right job. So let me give you this explicit example. We're going to simplify a heck of a lot of things, and I'll quickly say, get to the punchline. So remember our main, if we did all the work that we need to do, our main equation is the wave equation. And it's let's say we're doing harmonic formulation. Our main equation is given by this, like the principal part of the equation. And we work really hard to ensure that everything is nice so we can ignore the lower order terms. So but let's just give this very simple example. Suppose we're doing the same, but for a scalar field. Again, if we had a scalar field in our system and we're excising, we're also going to be excising the scalar field. We want to know, are we doing a good job, the right job for the scalar field? And this translates directly into the metric itself. So suppose our metric that I wrote over there with the indices down, and let's imagine this is a 1 plus 1, and I'm going to be abusing a little bit of notation because I want to make contact with that. So in metric, in matrix form, is like so. And then when the this up is given by because this is when it is in this up, this is when it is down. You write what this is, and the structure of your equation will be like so. So this is just that wave equation where A, B, and C are, well, the combinations, well, that's A, B, and C. Right, so now we know what to do. So remember, we have a second order wave equation, reduce it to first order just to analyze, compute the eigenvalues. Remember, we said that's how we're going to decide, do we have something that is sufficiently hyperbolic? We know it will be because of the structure, but let's see what the eigenvalues are. So go through this exercise. I'm not going to reproduce it here, but your eigenvalues will be the following. Okay, so let's just think a little bit about this. Suppose we're dealing with Schwarzschild coordinates. So for Schwarzschild coordinates, Schwarzschild in standard coordinates, beta is 0, so we don't have B, we just have A and C. Asymptotically, both A and C go to 1, right? If we go very far, that's going to go. So what do we get here? Well, the B is 0, so that's gone. We have plus minus something that is 0. And this A, well, this A goes to minus 1. So asymptotically goes with minus 1 over alpha squared. So what this is going to give us is, at far out, lambda is equal to plus minus 1. Now, as we go towards small r, the same thing will happen. So maybe C over A will give me something, but I still keep getting the plus minus, right? If we get a plus minus, remember what the eigenvalues also told us, where information is flowing to or from. So we're still, if we keep having the two signs, so we have at any point, some information goes this way and some information goes that way. If we excise at such surface, we're in trouble. Because there is information that wants to go that way, and we don't have the right to say, this is a boundary, I'm going to ignore everything from the inside, unless I put boundary conditions. And we don't know what the boundary conditions are inside of a black hole. However, these were a judicious choice of either shift changes things. Now you have this, minus 2b over a. Remember, a is negative. So this is putting a minus sign in here, and my counter that plus. And so then what you may end up with, so it's the other way around. So this minus with the a, that's a plus. So this is a positive. And this may turn out to be large enough to have something that at far distances have the two modes, and as you go inside, you end with that, right? Everything falling in, which is what you expect. Physically, this is what you expect. But if it doesn't happen, you are not moving your coordinate points in the right way. And so this is something that you have to be careful with. So if you're going to excise, one thing you want to know is that, do I have an apparent horizon, yes or not? And at that apparent horizon, is everything falling into it, yes or not? If the answer is no, then you have to change your gauge. Your gauge is not conducive for using excision. But if it is, then you're safe to just cut it out. So if you have a collision here, you find that there is an apparent horizon there, and all the eigenvalues say you're pointing in, then you're perfectly safe just cutting it out. I'm not going to evolve anything here because whatever the value at the surface of the apparent horizon is purely determined by what's around it. So that was the first comment about what we would do with a boundary. We still have to say, what are we going to do with this boundary? This may be our computational domain. And here's where it depends what problem you're solving. If you're solving the problem of gravitational waves, you're in asymptotic flat spacetime, you know that if you go very, very, very far out, the metric here should be rather mundane, very simple. There are ways of doing things in a more or less correct manner. You would have modes that go this way and modes that go that way. The modes that go from inside out, you know you couldn't touch, you do nothing to them. You have to provide information to the modes that go from right to left. But if there is nothing that should be coming from that far, then you can set them to 0. And roughly this is what is being done in all codes. There is a subtlety in that we are dealing with a constraint system. There are constraints that need to be satisfied. Even if I put all this to 0, I may be violating the constraints. So in reality, most formulation, in fact, I would say all applications, especially with BSSN, introduce constraint violation. This constraint violation will say there is quote-unquote crap that is coming in from the inside that is affecting the solution inwards. But if you put this sufficiently far, the size of that crap is smaller and smaller, and it only affects from here onwards. So imagine that you have a boundary here. This is boundary 1. This is boundary 2. So then you may affect, and you may be worried by all this. But if you move the boundary further out, then you're affecting only from this region. So the amount of region that you can trust well gets larger and larger. So what you do in practice is push it far out, which buys you more time with full control, and also says, well, also the time where you don't have extremely all under control, you know that what you have fed in is smaller and smaller as far as violations are concerned. That you can get away with as long as your question is, what is going on in astrophysical systems? I want to tell LIGO what they are seeing. What if you're doing ADS-CFT? There is you're out of luck. ADS-CFT, as you heard from Veronica and also Roberto, are trying to read off something on the boundary because that information is the dual or is going to be telling something about how the CFT is behaving. So no, you can't play these things. You have to be much more careful with the boundaries. Luck has it that ADS is very special. They have this potential, and essentially really nothing of important is getting that close to the boundary. And so by imposing that this boundary is anti-de Sitter, you can do quite good control on the boundary treatment. And again, I refer to you to discussions in the Chesler-Yaffe review and how they do it. And so they explicitly use that this boundary should be ADS to leading order, and then you can compute the next to leading order, and in case of ADS, it's next to leading order, where the true physics comes in, so you can gain a lot by actually imposing ADS and looking at what the sub-leading behavior is of whatever is getting to the boundary. Other than that, everything goes the same way, except that in order to have good control on this boundary, and here I'm telling you a little bit about the ADS application, and just also going back to what I said a minute ago. So they use a formulation that is a characteristic formulation that has the foliation using explicitly null surfaces. They excise, so if this is a black hole there, they excise once they go a little bit inside. They use the only residual constraint gauge freedom that they have is how you label these points or what's the coordinate freedom that you have along this null ray, so that this boundary is always at a constant surface, just for convenience. That's what they do, if you look at Israel, Chesler, and Yaffe. But if you read some of the papers I and collaborators have written, we don't do that. We let it flow, and we excise. And so we go a little bit, and if the black hole happens to grow, then we excise even more. And so our grid goes some distance inside, and then that's it. And it works very well. The characteristic formulation is very robust. For the problems you can do with it, it really is arguably the simplest, more robust option that you can work with. It takes away from you all gauge freedom. because the gauge, almost all the gauge freedom, the gauge is such that if you want these alpha and beta are chosen so that you ensure that these surfaces are always null. Of course, the formulation is very different, and let me just say 2 words about that. Remember when we wrote the wave equation in these coordinates, we had something that looked like this. I'm going to call it ux. Well, in this type of approach that you're using, say, time-like null foliation, the metric is more like so. There's something here, d squared. Well, let me call it C. It's roughly like this. Is how you write. Notice that you don't see a dr square. That's because it's a null. That surface would be null. Surface at constant u are null. When you plug these ansatz into Einstein's equations, you see there is a very different structure from the one you see in the 3+1 decomposition. You have a structure that basically says derivative along R, either the first or second order of A, B, and CA. So you have radial derivatives for A, B, and C. And then you have an evolution equation that looks like the one I wrote up there. Roughly of this form. So there is only, and this DAB is trace-free or has determinant equal to a constant. So essentially here you only have 2 degrees of freedom. So these are the degree of freedom, the true degrees of freedom of the theory, only 2. And the rays are constraints. And again, these are the constraints that come naturally by the fact that you choose that each of these slices is null. There is still a little bit of, as I said, residual freedom as to how you define these radial coordinates, but by and large, that's what you got. Again, if you have any questions, I'm happy to answer. But in virtue of time, I'll say the last two more things. So what is it? I'm under covering the questions I mentioned, but I'm just trying to give you at least a little bit so that if you're interested to go in that direction, I'm giving you the first kind of breadcrumbs in that direction. The last one was astrophysics. So in astrophysics, in addition to worrying a lot about the left-hand side, you worry quite a bit about the right-hand side. So this is where you say, I have matter. Let's say because I have a neutron star, I have electromagnetic fields. Because, of course, our neutron star is magnetized, and it can do a whole bunch of things. I also have plasma surrounding my objects. Like we see pulsars because of the interaction of the neutron star with the magnetosphere around it. We also might have microphysics. It's because you want to get your gold. You make 2 neutron stars collide, and you get a ton of gold. I mean, if you've seen it, like the collision of 2 neutron stars made about 2 or 3 times the Earth mass in gold, because we have to go get it because it's very far out. But all these things play a role in the dynamic. You might produce neutrinos that take away a heck of a lot of energy out of the system, and because it's doing that, it's a significant effect governing dynamics. So not only worrying about the GAB is key, but you also have to worry about what this thing and what the structure of the equations are. By and large, all of these have something beautiful. The equations come from roughly the conservation of the stress energy tensor. And when you look at what the variables here are and the equations that you end up with, they are coupled to GAB only through lower order terms. Remember, GAB has second derivatives of metric. Out of here, the metric comes in through Christoffel symbols, which are first derivatives. So as far as telling the problem, is it going to be well posed or not, you're good. You don't have to worry that much, by and large. You do have to worry about the physics. This is a horrible mess, and some of, like doing matter that is magnetized is very delicate. But I promise many of the discussions we went through also play a role. The main formulation for the magnetic hydrodynamics, ideal MHD, has all sorts of issues and all sorts of black magic to control the behavior of B, because astrophysicists, I have my friends, started with a formulation that is weakly hyperbolic. So they came out with numerical techniques that control that problem, but it was because at that time it wasn't fully appreciated the difficulties of dealing with weakly hyperbolic systems. Nowadays we know better, and so if you have questions, I'm happy to answer and point you in the right direction. And let me just say the last thing I was going to say, which was about beyond GR. So beyond GR, you essentially have, way too many theories out there. Just too many. So I can't go through them. I can tell you what the problems are. If you insist or somehow you land in an equation that is a system that will ensure that you have second-order equations, and the broadest, most generic family that you can work there with is Horndenski. So f of r theories are here, scalar tensor theories are here, a whole bunch of things. And then some of the ones that Claudia presented, they can all be accommodated one way or another into this family. The issue you have here, and Roberto earlier today mentioned that if you do a conformal transformation, you can write things so that it signs equations with a source, and it's a source that has a weird behavior. So in many cases, you can pull this trick. If you do the conformal transformation, you end up with an Einstein tensor with a source, depends on, say, a scalar field or a vector field. But that freaking guy has its own evolution equation, and I'm going to write it this way: gamma hat AB, say, grad A, grad B of phi, equal a whole bunch of things. The main issue is here. Here, this is not GAB, it's GAB plus something, grad A of phi, grad B of phi. So this is an effective metric that changes the evolution equation or the dynamics of this scalar field. It does something very interesting with that. If we had this, the propagation would be the same as in GR, or the same as the Einstein tensor. But because you have this allows some modes to propagate faster than others depending on what the field is doing. This is beautiful from the physical point of view. But we know now that this thing, acting on that, so that you have a second order operator for your field, multiplied by first orders. Remember, this is within the class of truly nonlinear problems, where our mathematicians friends will tell you, careful, you can have shocks, you can have high discontinuities, and worse yet, if this thing happens to change sign of the signature of that one, you might end up with a system that starts hyperbolic and becomes elliptic through its evolution, in which case all the initial value problem goes to heck. And I promise there are explicit examples where this is happening. So depending on how strongly coupled this field is, you may or may not be able to ask relevant questions. So this is something you have to be quite careful with, but it's a field of very active investigation. And the last one is like EFTs. So EFTs will give you equations that go like, again, RAB equal something. That something generically will have derivatives of your R, higher derivatives, and so on. The assumption is, so there's a coupling, of course. Of course, the physicist's assumption that went into writing these theories was, I'm in a regime where these terms are small, this coupling is small, they should not be changing things very strongly. The mathematician way of thinking this is, careful, what is it that you have? You have an equation that says phi comma tt, say equal phi comma xx, plus lambda higher derivative of phi. There is no guarantee a priori that these higher derivatives will stay small. It will depend on the nonlinear features of your problem. You could have written your EFT argument thinking, oh, I have this very smooth solution, I evolve it, but these nasty terms which are very nonlinear might take you into the UV. If that's the case, you get out of the regime of applicability of the EFT and you don't really know what to do. So I'm going to claim very strongly that all EFTs that are out there have that problem. The issue, however, is what we're doing. So we have to be very, very careful. It could be very well the case that your initial data of interest is something very smooth. And it could very well be the case that with that very smooth configuration, the system should behave nicely analytically. Numerically, we remember we have a grid. We're continuously pumping in a little bit of noise at very high frequency. It's noise that is outside the EFT. And so that one can take off and break everything, even though if you were able to do this computation analytically, you could have some control. So there is a tension here in how you actually do the nonlinear problem. Different people do it in different ways. One set of people think kind of particle physicists, we have done this over and over. We know what to do. We have some equation, let's say some E of something, some field, and we have some interaction which might be nasty, so let me call it N. So what we do is we solve this problem first, we get a solution, we put it there, let's call that 0, and then we find the correction. This is what typically they do in scattering problems, in high energy physics. So you have something that comes in, interacts, goes out, and you want to know how much this little correction push that answer up and down in some scale, let's say. If you're trying to do this with binary black holes that are colliding or whatever, something that's dynamical, this goes on and on and on and on. So the accumulation of that might actually give you something that is completely nonsensible. The secular effects might build up, and the solution you get from here might have nothing to do with the solution that you were trying to solve. So we have proposed some other idea. If you care, I'm happy to talk about it, but it's related with the last thing I'm going to mention. There is this already happens in hydrodynamic. So in relativistic hydrodynamics, if you include viscosity, you have tachyons, you have something that formally makes no sense whatsoever, mathematically. However, you can say, well, this is an EFT. I'm expecting my system not to go to the UV. I want to study here. How can I control that very high frequency nastiness that it has built in? And so they modified the equation such that that is well behaved. So you can extend this idea, pushing it further to the context of EFTs. And then it is a program that I claim, at least I'm sure that it is not the case that doesn't work. I claim that this one, I'm absolutely sure doesn't work, even though people do use it, because, okay, there is something, if you want to do it, you can do it. Okay, so let me just end with another quote by Boyd. So Boyd, I mentioned that quote, computation is something that should be resisted as much as possible. He has another one that I like a lot, and I tend to tell everyone to remember. That book is beautiful. It has to do with spectral method and has all full of cute things. I would refer you to definition 16. It has many. Definition 16 is the definition of an idiot. That's what, an idiot is someone who publishes a computation, a result of a computation without having done the convergence analysis, compared with a much deeper error analysis, so that you can make sure what you're communicating is correct. So don't satisfy the conditions of definition 16. And I think I'm going to stop here. So if you have any questions, I'm happy to answer.